Today we are going to talk about trees. I think you took one lecture about trees. Yeah. First of all, we are going to review the implementation of simple binary tree in C++ and C. Then we will have some applications to compute the size of the sub tree or the tree complete tree. I mean by that calculating how many nodes contained in this tree. And then two applications of computing the depth and height of a node. I think you already took this from the lecture. Just for a quick review, these are the terms we usually use for tree. We have the first node, we call it tree, root. And this starting from this node, we draw our rest nodes inside this tree. So here we have the root node 11, and then we will have the rest of the tree. In this example, this is called a binary tree because each node has only two connections, left and right connection. That's why it's called binary. You have only two connections for each node. And each horizontally you have levels. So at the root you have level 0, and then level 1 you have two nodes in level 1, 7 and 15, then level 2 and level 3. You have the term subtree. This means each tree has more than one subtree. For example, starting from 15, for example, you have a subtree contains 15, 30, 20, 12, 14, 18, 25, and so on. You can also choose a smaller subtree. And again, you have children. When you connect with your node in the next level, another node, you call them as children, and the one you start from it called parent. What else? And you have finally, when you reach to the last node, you call this node as a leaf. So this one in dashed node all of them are nodes. And the nodes which are not leaves are an internal node or internode. So you have three types of nodes: root, leaf, and internode. You have only one root, and you can have multiple leaves and multiple internode or internal nodes. Any question? Yeah. So just to have a simple exercise for such tree, how many nodes we have here? Can you count it? For this one, yes. Yeah, how many nodes in this tree? You should give me an answer. Then you can go and count them. No, how can you show me how you counted them? You can show me on the slides.
First root I didn't count it,
Mm-hmm.
and then there's nodes in there.
Mm-hmm.
I thought until the end of the nodes,
Mm-hmm.
this won't be internal, so I count them
Okay, so the answer is incorrect because when I tell you, that's why I asked you, when I tell you how many nodes inside this tree, you should consider all the nodes, the root and the leaves and the internal nodes. So the node is the basic concept, but I did not told you how many leaves we have, how many root we have. So you should count all the nodes. This is the total number. Okay, so in this tree, for example, I think it's 18, if I'm correct. So you can count all the blue dots, and these are the total number of nodes. How many leaves you have here? Let's go back one step. Do you remember the definition of leaf? Yeah, this one. So can you recognize the leaf? How we say this node is a leaf, or it's an internal node? No, it's not related to subtree. Again, leaf node is any node that has not any children, has no right or left connection. As this diagram states, all the nodes with dashed board, this board, called a leaf. Why? Because nothing is connected with them. I mean, to the next level. They only have parents, but they don't have children. So they don't have any right or left connections. So in this tree, all of these nodes in level 3 are leaves. Okay, is it now clear? Yeah. So here, which one? Can you show me? Can get to the?
There's 2 in here,
Mm-hmm.
and then 6 in here.
Mm-hmm. Okay. What about this?
Oh, okay. Yes, there is no children.
9.
So,
What
9
about
here.
this and this?
Oh, yes,
So it's 11.
yes, 11.
Yeah. So you should not make a false decision. You should see all the levels. So even it was in level 2, you have 2 leaves. You should also explore the next levels.
Yes.
Yeah. How many internal nodes you have?
2 here,
Mm-hmm.
3,
Mm-hmm.
4, 5,
Mm-hmm.
6.
Uh-huh.
Did I count?
Yeah. No. This 7. Yeah.
7 and 8.
Okay. Yeah. Correct. So 8 internal nodes.
Yes.
And for sure, the summation of leaves plus internal nodes plus the root should be equal to the total number. Yeah. Okay. In this slide, I'm just repeating an idea that tree is not, as a data structure, is not completely new. We are employing an old data structure we already know to build our tree. So can you recognize what is the basic data structure we use to build a tree from this graph?
I could not understand the question.
Okay, I'm telling that you want to build a tree, right? So I'm telling in this slide that it's not a completely new data type, data structure. We are reusing or employing another data set, a data structure. We already, linked list. Can you recognize how this is connected with? I mean, can you understand how this connected with trees?
With this head
Mm-hmm. Yeah,
connected with
but
other head.
it was one head, right? Here,
Yes.
two connections.
There is 1 and 2.
Why we have two connections here? If you can like link the ideas with each other.
It's connected with 2.
But two children's.
Yes.
Yeah, that's why we have two connections. We call it in nodes for tree, it's called left and right connection. So here C, for example, is the root and has right branch and left branch. And again, each node can also have branches to the left and right. So, and finally, when here, for example, this node 5 is a leaf. Why? Can you say why?
Because there is no connection.
Yeah, there is no children, so
Yeah, no.
it's null here. So from a programming perspective, once you have a node with for left and right pointers equal to null, this means it's a leaf. So this is we are going to see in the code. We will iterate through all nodes, and the node that contains for left and right the value null, this means either the tree is empty, so you are in the root and nothing connected with the root, so this tree is empty, you only have a root, or you reach to a leaf node that contains left and right equal to null. Can you recognize another nodes or another leaves here? We said 5. What else?
Two trees leaf.
Yeah, 2 and
2 and A and S is leaf.
no. Why?
No children.
But A is connected with Y, and S is connected with both, with 2 and A.
Oh, okay. Yes. So why?
Y, yeah. Y is correct. 2 is here. We have only Y and 2 and 2 and 5. Here you cannot consider it as a leaf because it's correct that the right branch is empty or it's null, but the left one is connected with another node. So this one is you cannot consider that as a leaf. This one, A, if you stay focused with A, it's similar to this one. To this one. It has one connection, but this one is not leaf. This one is a leaf, but this one is not a leaf. Yeah, that's why this one has one connection only, but it's not a leaf. This one is a leaf because the both connections are null. Okay, so this is the structure of how we are going to implement the basic node of a leaf. Let's see it as a code, Visual Studio. Yeah. So if you remember, can you remember the node we used for linked list? It was something like struct node, and we said, for example, it value or integer data and next, right? Something like struct node, yeah, next, something like this, right? So we are going again. The tree has a basic building block with linked list. So this is the linked list. How we are going to evolve our design? Again, we will have two pointers, right? Which was left and right. So this is very simple. You only add one additional pointer. Instead of having next, you have now left and right. I do prefer using, this is struct if you want to use the C, but I do prefer having a class as node. These are public, but again, you have the option, complete freedom to use C or C++. And now we are going to define the constructor. So when you will create a node, what you should pass to the constructor? Exactly. So here you just pass the val to data and give left null and right also null. Next session we will have another method. We will call it insertion, and here we add value like int val, and again value can be float, can be double. Let's just to change some. Can be float. Here can be float. This method will be next session because it's related to the theoretical part, which you did not take this week. This way this function or this method will handle how you connect the nodes. I mean, when you add, you already have a tree. You need to have a way to find which the best place to add the node. I mean, you have different options, like in this, for example, in this tree, you can add the node here, or here, or here, or even here, or here. You have multiple options, right? So next session, after you will take the next lecture with Abdul Hafiz Hojan, we will find how we can implement the insertion. So let's go back to the code. In this session, we will use the manual way by doing the connection by ourselves. Turn 0. First of all, we're going to build the root node. So we will say node root, and here let's also give another option for node without value, like this. So you can even put here 0, for example. But anyway, we are not going to do this. Node star, because we are going to use new. It's up to you. You can use. I mean, like this, just a node root like this. But we are going to use a new node and pass a value for the root. Let's say number 1. Okay. So let's say we want to here we want to build this tree. Yeah, and then 3. So can you tell me how we should do this? And next, right of what? I mean, look again. 2 is connected with 1, which is the root. So here, how we should say? Root. To what? Left. This one is left. Equal to n1, because you are going to store the address of the node, right? and n1 is already a pointer, so left equal to n1. What about the 3? Equal. Mm-hmm. Mm-hmm. And now root, what we should say here? Mm-hmm. Exactly. Now we finished this level. We're going to 4.
Statement, we have to clarify this, what should I say, the parent.
For 4.
Yeah,
Plus 4. Yeah. So let's first create the node. Call it n3. Okay. Now. Actually, okay. Tell me.
I guess we will use, I don't know if I'm true, but we will use 2 to 4.
Exactly.
And 2 to 4.
Because it's, it's a linked list, right? So you already root is connected with n2.
Yes.
So you simply can say n2 to the right equal n3. In the same way, you can also say root right and then right equal to n3. This is identical. You can do because this one root arrow right is the same of saying n2. Okay, and then equal to n3. So you can do the both. It's better to say it like this, but you can also do this. Okay, so and there's no need to explicitly say to n2 right. Oh, sorry, here should be left, not right. Yeah, and here left. Oh, I mean all of them are left. Left, left, left. Left. Left, yeah, is correct. I think we just should be here n1 left, because n1 is equal to 2. Not the 3. 3 is this one. 2 is n1. So n1 left, and this one is correct. Okay. Just to go back, the null is the default value for left and right, so no need to assign the null value for n1 and n2 and n3. So by doing so, we defined our tree like this one using the code. Is this one clear?
Yes.
Yeah. And again, here is like the way of handling the access in this way is very basic. It's a very simplified way. We will have better methods next week or next session, because next week we will not get a session. So the task of creating this tree is completed. Let's see what's next. Here I'm just saying how you implement this, and after you have the node, which is this implementation, or using class. Okay, search. First of all, let's see this animation. Let's say we have this tree starting from 41. We have a special condition, like this tree is ordered. The mean of ordered that you can see here, 41 is the biggest value. And then sorry, not the biggest value. When you insert a new value, the right branch always have a bigger value. I mean, 41 is the smallest value between the right branch. So any value or any node in the right branch is bigger than 41. The left branch is in contrast. All the values are less. Exactly. This tree, you will find this tree in the next lecture. This called binary search tree. But in this session, lab session, we are not going to explain it. We just going to consider that we already have this tree that's ordered. I mean by ordered that right branch has greater values and left branch has lower values, and each subtree is the same. Like here, 65. Again, the values on the right are bigger. The values on the left are smaller. You can see. So any subtree has the same way of organizing the branches. We go to each node, and the right node should be bigger, the left node smaller. Okay, it's the same thing in the left branch. 20 is less than the right, but bigger than the left. And you can have only one node for a branch. For example, the subtree 91 has two nodes, but the subtree for root node 29 has one node. So it depends. So and by the way, if you can use this website, they have like visualization for many algorithms related to trees and other data structures. So you can check this website, Visual Go, actually Visual Algo, or it's like combination between visual and algorithm. Okay, so it's back to the code. Based on this fact, or using this fact that always the right branch is bigger than the left branch, we can define our own search function. Let's say this will the search function will return for us maybe a value or even a pointer to the node. So we can say node star search. We will pass the root. Yeah, actually you can pass the root, or okay, in this you can like enhance your code and add here like node star. You remember the head in the linked list, so you can say here like root. I mean, if you remember in linked list, we have like always we have node head. Remember? So I'm this time also we can say node star root and assign for this the first node for us, or the other way to pass the root explicitly to the search. So if we have here the root, there is no need to say to pass the root to the search. We only pass the value we are searching for, like int val or float. Here we have float val. Okay, so for now just we will not have the root, so we will pass the root to the function. Is it search?
Search right is important.
Search right?
Right is important. You write along, so.
Okay.
So
Yeah, no worries. Like this. Okay. So let's start from the simplest thing. We are going to use recursive way of implementation. Recursive, you remember the function call itself. Okay. Did you took the concept of recursion before? Okay, but we already use it multiple times. If you remember, even in linked list, do you remember in linked list we used this concept before, that the function call itself? So here we will say once if root equal to, actually it's better to say node, not say n, because when we use it as recursive, the next node is not a root. So let's say when n equal to null or n to the left and n to the right, both of them equal to null. Actually, this one process the condition of having empty root. This one for the condition of reaching a leaf. So you have the right and left as null. So in this case, you just return.
So if left and right is null, there's only leaf.
Yeah, it's a leaf. So you reach to the final destination. Okay. Here, if if n, we call it data, right? Data is bigger than, sorry, if val is bigger than the data of the node, this means you should go to the left, to the right, sorry. Again, if you remember, we have the right branch which always have the bigger values. So if the value we are searching for is bigger than the current node value, so we need to go for the left. Now the sentence of going to the left, here it is the recursion. So we will call search again. Why I writing it? Search, but now I will pass the n. What? I mean, search have two arguments, right? No. Data is fixed. This one is value. There is no change. But here, what you should pass? We said we are going to the left branch, so to the right branch. Sorry. Exactly. So right. Now else, this one is like, just to remember, this is the right branch. Here is smaller, so we go to the left branch. So else we go, we say search. And here, yeah, okay. And we also need to say that if, yeah. No, because you already. Sorry, left. Yeah, sorry. Yeah, it's just a misspelling. So when the value we are trying to search for is bigger, again we go and search for the right branch. If it's not, or it's smaller, so we're going to use the left branch. And here we need to break the recursion either if we reach to the leaves and we did not find anything, this means this here, either it's empty or we reach to a leaf without finding our node. Here, if n data equal val, then return what? Again, we are searching for, no, there is no name leaf here, so return n. Okay, so this is the code here, the same. Actually, we can here merge the both conditions in one, or you can just do it like here. You explicitly have two conditions, or if it's empty or the root has directly the key, you can return the root. And here is the recursion. If the key here in reverse, if the key is, yeah, no, it's the same. Here we just wrote it in the reverse, value greater than in node, or in the key here is smaller than the key we are searching for. And by the way, we in most cases we call the value or the data here for the node, we call it as a key. Here we call it as a key. This is usually used term. Okay, so when you're going to read this code, you can, the key is the data or the value of the node. So here, whenever you reach to the root is the same here. We node n. So whenever the root is null also it combines two meanings. The tree is empty, or you reach to a leaf, or the value of the key value of the node you are currently in. I mean, when you do the recursive, the root here does not mean the root, the one root here. It's the root in the recursion level. Whenever it's equal, you return the root. Whenever in any level it was in, it does not matter. Whenever the key you search for equal to the key of the root, the node you are in it right now, in the recursion level, so you return the root. And here you are actually doing the recursion. That means you check the value of the key. If it's bigger than the current key value of the root, you search for the right branch. If it's not, you search for the left branch. And here is another note. If you saw here in our code, here we implemented, we said else, right? Here we did not said else, because we have return. This is two ways. Yeah, there's two ways of writing code. Whenever you use return, that means for sure it will pass to this. Yeah, exactly. So no need to say here else, because for sure it will not complete the code. It will just break the code and go to this search. So it's up to you. That's why I presented another way, so you can like write your own code. You can use your own code, your own way of expression, as long as you can do the job required from you. So you either use a simple code like this, but it may not be very clear for you, or use the same code of here that we explained many conditions instead. Okay. Is it clear? This is another application. We are trying to calculate the size of tree. I mean, the size of tree is the number of nodes. So we simply iterate with the tree. If the tree is empty or you reach to the last node and node is null, you return 0. Other than that, here needs some explanation. Look, yeah.
Is this for deciding the node to the left and node to the right? I mean, they're calculating left and right. Then plus one is root.
Yeah, actually, yeah, it's the same because when you don't have any branch, I mean, it's actually this combines many things. When you do iteration, using recursion, you have many options. I forget my marker pen. Let me draw it. So you have here like a root. You have other nodes and another nodes. And here, let's say we have one node. So when you start like iterating with a node, you start with this node. Let me change the color. We start here. We check the value of this node, and this node is not null because it's created. Now we go to the left and the right. If you remember here, return. Okay, not this one. Return to the left and also size right. Recursion here, recursion to the left and to the right. So let's left and right both has values. So you call the search here. You have now in the queue search. Let's say the search. Oh, okay. It's hard to draw it here. Now let's say we are in the left. So this node also has branches, right and left. So again, you can go now to here, and you can go to here also. But now you called this node is not empty by its own. It's not empty. But no, yeah, left and right both are them when you pass the size. Yeah, exactly. Let me close this one. Exactly. So when you call size left, now let's say, imagine we are here. When you call size left, so this one is null. And when you call it right, this one is null. So both of them are considered in this condition. So this condition like cover many cases. So either if the empty tree or you reach to here. Another case, let's say now we are in the right. We pass to here. Here, when you call this node right, it's not empty, so it's okay. But when you call left, no left, so it will just return 0 for you. Returning 0 in this application because you are counting how many nodes in this tree. So if we want to like what we call it decompose this return or decompose the stack of recursion we have. Actually, here we have 1. It will return 1, and 2 calls. 1 call for the left and 1 call for the right. Now the call in the left here will return also 1 and 2 calls here and here. Here, now we are in this level, so it will return only 1 and return also 2 calls, but these 2 calls will be 0. So 0 plus 0. Here, also 1 and 0, 0. Now here, we already now counted this. This will return 1 and 0 and 1. So if you count this 1, 2, 3, 4, 5, and 6. And this is equal to the total number of the nodes in this tree. Okay, so it's clear? Yeah. Let's go back. So this is one application of a function we can write for the tree to count the number of the nodes. And actually, like using the recursion here is way more simpler than writing the code with if else. I mean, you have if you check the size of how many numbers you have to represent this function to calculate the size of the tree, the total number of the nodes, it will be very smaller than considering if else. Like, let's discuss how we do this in the simple way or in the normal way without using recursion. You need to iterate using a while loop, and you should start from the node left and right, and then iterate for each one of them. But this needs more conditions, more if and else and loops. So you can like squeeze the code, compress the code with just 4 lines using the recursion. Yeah. And especially in this chapter for the tree, almost all methods will be represented with recursive way. This is another code to calculate the depth and height. If you remember the depth, the definition of the depth of any node, it's how many edges or how many connections between it and the root. So this is the depth, and the height is the let's say the longest way that connects the root with a leaf. So you may have, like, let's go back, you may have different roots, different leaves, but the one we are considering to calculate the height is the one that has the longest way for the tree. So for this tree, you can see the leaf, we have two ways that are the longest, here and here. Both of them are equal. So this one is the height of the tree. So how we going to do this? Again, we're going to use iteration in recursive way. Here, the first condition is again the one that will break the loop, will break the sequence of the recursion. Whenever you reach to the, actually you pass the root node to this function and pass the node to it. How you pass the node? You pass the value of it. I mean, like for a tree like this one, you call the depth function and say depth, the address of root, which is address of node 1, and the value of 4, it will search for it. So here why we check if the root data, and again, root here does not mean the root. It does not mean it's the root node. It's the root node inside the iteration. Okay, because you call depth many times here and here. So each time you pass the left or the right. So here root, the data of root does not mean only the root, the first one. It's the first one or the second one or third one. It's any root, it's any node equal to the level of your iteration. If it's equal to data, so you return 0. Unless of that, you go to here. It's like, if you remember, it's very similar to counting how many number of nodes, because you are calculating the depth. Yeah, adding 1. So here you will return 0 because you are not going to add anything to the sequence. So you either add 1 here or 0 from here. If you did not reach to the node you want, you add 1. If you reach, you add 0. And actually, if you check this code is exactly the same of search. You remember search here? We check the value key. If it's bigger, we go right. If smaller, we go left. If you go to here, it's exactly the same. But here you are calculating the depth. There you are not, look here, return without 1 plus something. You're going to return the address of this node when you reach it. So actually, this function can be represented also with search function. You can write it with the search function, but for simplicity, we will rewrite the code again. So when the data you are searching for is bigger than the current node or the current route, if it's bigger, then you are in the right. You should go to the right. Again, because this tree is ordered. We can consider that the tree we are using is already ordered, like the one I showed you here. So if the data is bigger, we go to the sorry, it should be the left, not to the right. Here it's incorrect. Yeah, here it should be to the left. Just this I will correct this later. Or let me correct it now. This one is left. Okay. So if it's the data we are looking for bigger, so we go to right. If smaller, we go to the left, and we add 1. If we want to go to this tree, let's say we want to calculate the depth of this node. So this is our target. Okay. So the depth, we have depth function. It starts with the root. The value here, we check the value of the root data. It's not equal to the data here we are looking for. So it will not return 0. It will go to these conditions, if and else. Okay, we check now the value we are searching for. Is it bigger or smaller? Let's say it's smaller, so it will go here. This node is not equal. Again, it's not equal to the not equal to data, so it will not. So it will check the conditions. It will smaller. It will go to here. But again, you remember it. We have 1. Like here, we have this one means we have +1, and here we have +1. Until we reach to here, and actually the root data here equals to the data, the key we are searching for, or to the data we're searching for. So it will return what? 0. So it will be 1 plus 1 plus 0. It will consider it as 2. And actually, just a small note, some references consider this as 3 because they consider this root as 1 plus 1. So here you can say return. You should add, after you get the result, you should add 1. Some references, but actually there is no need to do so. So the depth of this node is equal to 2. You have 2 edges between this node and the root. Okay, it's clear. The next application is calculating the height. The height is very similar to the depth, but you are not specifying. You don't have option to specify a node. You represent the height of the tree with 1 number. It will not. I mean the depth for each node, like in this example, each node has a depth. So in this tree, this can be a question. For example, The depth in a tree can have one value or multiple values. What you choose? Multiple, because each node has multiple values. But the height of the tree, it has one, because it has only one longest way connecting the root with the leaf. So the depth, the high or the max depth can be also called the max depth. You only pass the address of the first node or the root. If it's null, that means it's 0. And again, because you are passing the left or the right. This breaks the iteration. Like the search function, like the depth function, the first condition will break the loop for you. If it's not, actually here, like, can you find like a note here? Can you mention something here? We can remove the else here. Yeah, because we have return here, so no need to say else here.
It says like it's initial left depth and right depth, and we have if condition if L depth bigger than right, then we will add the 1 because of the loops, so it will be 8. But if right will bigger than left, then the 8 will be right and plus 1 because of the loops.
Actually, you are correct. Yeah, you check you initial this. Actually, yeah, you are correct, because this value is going to be created each time when you have int something inside the function. This variable is local, so each time you will create it again. So each time you will create this variable and call the function, and then return this value. This value, return LDEPS, is the one that it will be reserved in the queue, in the stack. Sorry, I mean recursion is stored in the queue. I mean, when you have something like this, you will have a stack, not a queue. Sorry, you have a stack, and each call will only store the return value. Okay, so here, from all the body of this function, you will store in the stack the value of return. That's why we will have like final answer. That's why we have 1 plus something plus something. So each call you will have a result from it by a return, either 0 or 1. That's why we have like 1 plus 0 plus 1 plus 1. It depends about the execution here. The same way here, you just initialize a new variable called lleft and rleft. Sorry. Yeah, so you initial a new variable and call the function. And when you call the function, you either have return 0 or you have return the current value plus 1. Okay? So in this case, let's go to
Left and right is equal.
actually obviously it will return if it's equal, it will return the right, because in this condition you are checking left and depth. Yeah, it's so in this case it will depends about the order of execution, as long as they are equal. Yeah, so in this case you have like the highest depth or the max depth or the high of this tree is this root, like this, using this root. So the iteration, first of all, it'll check the call of this max depth. Is it null? No. So it will not return 0. It will go to here. You will have two variables, L and right. you have now one, let's make blue. You have one going to the left and one going to the right. It will check. Did you reach? No. So you will return, both of them are equal. So you will return 1. Now you have 1 here. Now you go again to this node. You go to the left and the right. You have now here. Yeah, you have now here. You are reaching here to the null. So you have here +0, and here +1, and this one is equal to 2. You continue the recursion. You go to here. You go +1, and you go. The right branch is null, so it will return 0 here. But here it will return +1. And here it will return +0, and the answer, complete answer, it will be 3. Actually, this explanation is not complete because the recursion in this example is more complicated to be explained like this one. Because this, as you see here, you should consider all like all nodes. It's not like here in depth you was searching for a data. We were searching for a specific node. So we used the consideration I told you about, that the tree is already ordered. So we have we know our way. We either go to the right or we go to the left, depending on the value, right? So we should not search for, or did you took the was traversing algorithms with Dr. Abdel Hafiz? You took it. Yeah. So do you remember why we use these algorithms, the traversal algorithms? The complete all algorithms for traversals are used to access to all nodes. I mean, like let's just to remind you. Sorry. Like this one. In all algorithms, you have access to all nodes. I mean, if you counted the nodes in each algorithm, it will be equal. Like this one, you access to the, if you check, to the 7 nodes, and here 7 nodes, and here 7 nodes. So in traversal, you need to access to all nodes. But for search, for example, going back to the search example, you know your route. So you started like here, you started by 41, you checked the next value, you found that the value you are searching for is bigger, so you go to the right, and then you checked again, and you found you are searching for 72 here example, so again you go to the left. So you know, like you have like points telling you that you now go to the you should go to the right, or you should go to the left. But in this case, when you want to calculate the height, you should consider all the ways. Okay, so there is no specific way to know that left or right has the highest or the longest way, because high is the longest connection between the root and the leaves. So you need to iterate with all nodes, and this code cannot be explained as simple as what I showed to you, but it's relatively how it's working, relatively. You already studied this with. Yeah. So, but this is another example. Let's draw this. Let's take this the expression and draw it together. let's have a new one. Is it clear for you? I mean, was it clear in the lectures? In the lecture, you said you already took it. Yeah.
Yes.
The same example?
Yeah,
different numbers.
Different numbers.
Yeah.
Yes.
This will make the thing more easier for you, or more, you can, by solving many exercises, it will be more easy for you to solve it in the exam. So again, if we want to express this mathematical expression or operation using tree, we should know first the priority of executing this operation.
So I guess root is the root of the binary
Should be
I forgot
division.
division. I forgot.
Yeah, that's correct.
The second left and first left will be multiplication,
That's right.
and then we will again left.
Because this one is this one, and this one is this one. That's correct. Actually, I personally I prefer to start from the bottom. They go up, but it's already it's correct to use this. Now
Now left is
addition.
addition, and then the minus,
Mm-hmm.
and we will left and right again.
But by the way, you made a mistake. But actually, it's a simple mistake. Now here 5
5 2
and 2.
and 2 1 for the right.
Actually, but you okay, not a mistake. Sorry, I thought this one is another division. Okay, now 2 and here 1. Okay, here you have now you first here is
One is 8,
exactly.
and there is no children for right.
Actually, there is a children, but it should be minus.
No, for the 8.
Okay, yeah, it's we reach to the. Here is the minus, and the right one is
We have now 1,
exactly
and then 7. No, yes.
7 and 2. That's correct. You well done. So starting from the bottom, it will start from here, from 7 minus 2. It will get the answer. Then you will get, because the priority will, you should like start calculating the numbers inside the arrows. And here is an arrow inside an arrow. Here is just one arrow here. Here one arrow. Here one arrow. But here you have an arrow inside an arrow. Here the simplest, the internal one, and here is the external one. So you start by 7 minus 2, and then minus 1. You have now like you have now in the level of the other operations. And then you calculate this level, and then calculate the other level, and so on until you reach here to the result. So again, it's our solution is identical to here, the same way represented here. We have exercises. Actually, I intended to have like 30 or 20 minutes to discuss the presentation and the solution of assignment, but you did not submit it. So let's discuss the exercises for next session. First exercise, in the same way of the depth and max depth and search assignment, you will write a function to sum all the values inside the row inside the tree. So whatever values inside, you should do summation for the values, and I think, yeah, and I think this one will be solved in similar way of max depth, but you should change in the body, or you can do it with your own implementation. And even if you are not going to do recursion, it's okay for this exercise only. Here you must return the max value, and this one should be using recursion. This one, and you can pretend or assume that the tree is ordered like this one. I mean, the right, this one, sorry. The right branch is bigger than the left branch in finding the maximum value, Okay, is it clear? The third one is for printing all values that are less than a certain value you pass it to the function. So let's say here in this tree, you pass to the function, let's say a value of 25. So it will print for you 20 and 11 only. Okay, if you pass it like, let's say 50, it will print for you 41, 20, 11, 29, and 32. It needs some like concentration, it needs some considering some cases, because if you choose it from the right, from the left branch, it will be easy, because you will check here like 29, only 20 and 11 are smaller. But here, whenever you get a value from the right branch, it will consider all the values in the left branch. Okay? Do you get it? I'm helping you to solve it.
Can I see again the
Question, yeah.
Okay, so I will check all the values and print all the smaller than. I mean, if I check 29, the program has to print less than 29.
29, yes.
Okay.
Yeah.
So I will do this for all values.
For all nodes, I mean, for any value, you pass it to the function. Okay. So I think that's all for this session.